Good afternoon, Evan Snyman here for Umaghloko, Making the Difference. Euclidean Geometry, Lesson 2, we're looking at the midpoint theorem, which we covered in grade 10, leading into the proportion theorem, which is a key theorem for grade 12. Now, one of my biggest problems with geometry is we do not realize that it actually is quite an intuitive concept and is very often only taught as an abstract idea of lines and angles and points on a diagram. So for me, the midpoint theorem says quite simply that if you were to take a swimming pool, as we have in the diagram, and I was to start over here in the middle of this side of the swimming pool, and I was to swim across the swimming pool parallel to the base side of the swimming pool, where do you think I would end up? And I think that many of you guys who got a sense of a swimming pool would agree that I would end up on the far side, also in the middle of the swimming pool. Now, this would be the same if I was to use, for example, a soccer field or a rugby field, for example. But again, it doesn't make a difference where I start on the swimming pool or the rugby field or the soccer field. If I started on the middle of this side, such that I was now halfway across the field, and I ran across the field parallel to one of the sides of the field. Again, if I ask you where do you think I'd end up, I think you'd agree that I'd end up in the middle. Now, this actually is a very intuitive concept and makes sense if you think about it. Now, what I'd like to look at quickly is the proportion theorem. The proportion theorem says roughly the same thing, except like with the swimming pool, it says that if I was to start, instead of starting halfway along the swimming pool, I was to start, let's say, 1/3 of the way along the swimming pool. So I start there such that I'm 1/3 of the way along the swimming pool. So there's 1/3 of the swimming pool to my left, 1/3 of the pool to my left, and 1/3 of the pool to my right. And I expand across the swimming pool parallel to the one side of the swimming pool. My question to you is, where do you think I would end up? And what I'm hoping you would agree is that I would end up over here, again, in proportion 1:2, or in other words, 1/3 of the way across, in this case, from the left-hand side. Now, this idea works equally well if I was to slice this rectangle in half. And so if I was to slice this rectangle in half and to remove this top half of the rectangle, it would still be true. I would end up on this far side of this triangle in the ratio of 1:2. Now again, you can see, hopefully, that these two lines are not the same length. I'm not saying that the piece of the line is 1 and the other piece of the line is 2. I'm saying that the proportion of this line over here is 1:2, whereas the proportion of this line over here is 1:2. So again, what I'd like to encourage you is to try see some of these geometric theorems in a more intuitive sense and not just as an abstract concept. So what the proportion theorem says is that if I was to have this triangle and it is cut by a line that is parallel to the third side of the triangle, it is starting with point D on line AB and point E on line AC, such that if I said that this line was, I don't know, let's say that this line's total length was 20, and I was breaking it up in the ratio of 1:4. I'm not saying that the line length BD is 1 and that the line length AD is 4. I'm saying that 1/5, again, think it through, 1/5, that BD would be 1/5 of AB, and that AD would be 4/5 of AB. Again, I'm not saying that the length is 1 and the length is 4. I'm saying it is 1/5 of the total length, and that AD is 4/5 of the total length. Yes, I know that we could calculate that. That means that the piece is 4 and 16, but that is not important at this point right now. What I'd like to say is we can therefore conclude that because this is in the proportion of 1:4, and this pair of lines is parallel, I would expect that even if this line here was 25 long, that I would end up with this break being in proportion of 1:4. Okay, that EC would be in proportion to AC of 1:4. Again, not saying that EC is 1 unit or 1 centimeter or 1 meter long, simply that it is in the proportion of 1:4. That allows me to realize that EC will be 1/5 of AC and that AE will be 4/5 of AC. And the key concept here is that what we have is that AD over DB will be the same size fraction as AE to EC. And as we saw in the last time, things that have got equal fractions we would say are in proportion. So again, intuitively, if we were to think back to the example of either the swimming pool or the rugby field, if I was to start in the second lane of the swimming pool out of 8, and to swim across the swimming pool in a straight line parallel to the one side of the swimming pool, it should not surprise you that I get out at the far side of the swimming pool in the second lane of the 8. And so I've swum across and kept, and therefore the two sides have been kept in proportion. 2/8 on the one side and 2/8 on the other side. This is equally true for triangles if the one side is parallel to the line that is cutting across the triangle. Okay, now as I said to you, this is an important theorem because it is one of the 2 grade 12 theorems that you need to know off by heart for matric bookwork. And so again, if you understand that one of the components of your work is to know proofs, and there are 4 from grade 11 and 2 from grade 12, of which this is one of the 2, then, as I said, this is an important one to study. Again, there is some back knowledge that I'd like to go through with you, and that is that triangles with the same base between parallel lines, now please remember these 2 things are parallel, so triangles with the same base between parallel lines, okay, so if I was to draw these 2 diagonals in, I would be able to see that triangle that I've highlighted here in orange and the triangle that I'm now trying to highlight here in blue, okay, these 2 triangles both have the base AC, and because they are between the parallel lines, they have the same height, and so I know, if I think about it, that the area of triangle BDC must equal the area of triangle BEC. They've got the same base and they lie between, and they've got the same height. In this case, I'm working with the, as I said, the orange one, which was BDC, and the blue one, which was triangle BEC. Okay, so that was a theorem that was covered in grade 11, hopefully with you, that if triangles have got the same base and the same height, they must have equal areas. A second piece of knowledge that I'd like to work through with you is the idea of what happens if I have triangle, if I compare triangle, the blue triangle over there, to this red triangle over here. So I'm looking effectively, no, I don't know what I'm doing. So what I'd like to look at is effectively redraw this, and I have a situation where I have that I've got here, and there I've got this line going to BE. So it's A, B, C, and there is E. And as I've drawn it with color coding just now, I'm talking about the blue triangle over here and the red triangle over here. Now, again, remember that triangles don't have to have a base that is horizontal. The base can be any side that I want. And therefore, if I choose to have the base as being BC, then the height will be from the altitude, the height will be from the side BC. But if I was to choose to use this side as my base, then my height would be this side over here. It would be coming from angle B down to the bottom here, as long as it is doing so at right angles. Well, that means that if I was to take the red triangle would be the area of the red triangle would be equal to the area of the red triangle, which is ABE, would equal to half times the base, which would be AE, times whatever we call this black, this line over here. So let's just call this H. As a result, we can also see that the area of triangle ACE would be a half times EC times H. And that these two triangles actually have the same height, because the distance from this baseline to the top vertex, or to sometimes called the apex, is given by this vertical line, as you see here. It is at right angles, this vertical line here, which we have marked H. Now, again, whereas in the top case, the two triangles had equal areas because they had the same base and the same height, here we only have the same height. Their bases actually are different. But this leads to an interesting observation. This leads to the idea that the area of triangle ABE divided by the area of triangle ACE, well, if we wrote it as a half AE times H and a half AC times a half EC times H. Sorry about that glitch. Cool. It would simplify down to being AE over EC, because these pieces, the halves and the H's, would cancel out. Okay, so what this now allows me to do is to set up my proof as I'd like to do. And so what I'd like to do is to have a look at that proof. So all proofs have the following situations. They have a thing which is given, a statement of what I am required to prove, a consideration of a construction. You don't always have one, but this particular theorem does have a construction, and your actual proof. Now, I'd like you to get used to this idea that all formal proofs have this layout of given, required to prove, construction, and proof. So now I'd like to look at the formal proof of the proportion theorem. And so starting again, we've been given triangle ABC with line DE parallel to BC, and we'd like to prove that the two sides are cut in proportion. Again, all formal proofs, and this is one of the two that you need to know from a trick, along with the 4 from grade 11, should be laid out using the structure shown on the left here. A statement that is given, of what is given, a statement of what is required to prove. I've abbreviated that down to RTP, required to prove. Any constructions that you may need to make. You do not always need to make a construction, but this particular proof does need one. And then the actual formal proof. So in this case, I'm going to literally write down what I was given. So I was given triangle ABC with D on AB and E on AC, such that DE was parallel to BC. I'm trying to prove that AD over DB equals AE over EC. And again, I do need to make a construction. My constructions here are going to be the two lines BE and the line BC. So I'm going to quickly label those in. I construct BE and DC. My proof follows from our earlier discussion on the previous slide, that if triangles are on the same base and between parallel lines, they are equal. Just now I used a slightly easier example and discussed the two triangles with base BC. This time I'm going to set up the two with base DE. So triangle DEB, its area is equal to the area of triangle DEC. They lie on the same base and they lie between the same parallel lines. So same base, same height. I can also show that by constructing the heights in here from vertex E, let's get that to be roughly perpendicular to the other line. There we go. Let's take that as being perpendicular. We can see that using the same ideas from the previous slide, we can see that the area of triangle ADE over the area of triangle DEB is equal to AD over DB. And in the same way, looking at it from the right-hand side, so this is looking at it from the left, if I was looking from the right-hand side, I can see that the area of triangle ADE over the area of triangle DEC equals AE over EC. But again, for those of you who can't see it, I will now try to draw it in, and maybe this will help make it a little bit easier. What I've drawn in is I'm drawing in this case, the height that is coming down from vertex E, vertex D. And so what I'm talking about here is that if I was to use that as my height, you can see then that these two triangles on the right side have the same height, the line that I've drawn in black. What this now means is, if you think about it, in these two triangles that I've written here, in these two statements I've written on the board, we know that these two are going to be equal to one another, because those in fact are the same triangles. Those are both triangle ADE. Well, if we look at the lower side, the denominators of these two statements, we can see that this statement, area of triangle DEB, is the statement I've got over here in my opening statement to my argument. And that this statement over here, area of DEC, which is in fact equal to the orange statement, or the orange area, is simply the denominator of this statement. Well, if these two green things are equal, these two green areas are equal, and the orange area is equal to the red area, then it must follow that these two areas themselves are equal to one another. And so what I now have is a situation where I can see that these two things are equal to one another, see that these two things are equal to one another, and as a result, it must follow that AD over DB equals AE over EC. Now, again, I don't mean to be too critical of my own layout or of my own argument, but it does bother me, and it should bother you, that my middle statements don't have reasons, and so I'm going to supply the reasons there, and that is triangles with the same height. And what I now have is an argument that you can't refute, starting from start to finish, saying that if this triangle is cut by a line that is parallel to the third side, that this line would cut the two other sides in proportion. And again, equal fractions means in proportion. So showing that AD over DB equals AE over EC, and that's a C, means that I've proven what I set out to do. Thank you very much.